Okay, good morning. Okay, can you see my slide? Can you see my cursor moving? Can you hear my voice? Just want to check.
Yes, sir.
Okay. Okay, so very good morning. So today we will do chapter 7, part 2 on energy analysis of the closed system. Okay, so before we start, I just want to give a short announcement. Okay, so for this week only we will have today's lecture. And we will, since most of you are not around, so we are doing it online. Okay, so please listen back to whatever we have learned today so that you will get a better understanding on chapter 7 part 2. So I didn't give a add puzzle video for this, but I just want to cover it in the class. Okay, so apart from that, the other announcement, so we will start to our lab 3 next week. Okay, I already uploaded lab 3 module in Google Classroom. So please look at it. And we will do the physical lab next week. Okay, so next week we will have a physical lab in mechatronic building. Okay, so I will tell where is the lab later. Okay, it's a different lab from the previous one. So now we will be in thermodynamic lab. Okay, so we'll do a short experiment on the thermodynamics. Okay, then another announcement is on your lab 2 and lab 4. Okay, so lab 2 Bernoulli's equation and lab 4 heat transfer. So open-ended lab. So I already given you before lab 2. Okay, and the due date will be end of the month. Okay, end of the study week. Okay, so now we have entered week number 11. So you have around 4 week inclusive of this week for you to complete and send. Okay, and I also given you a lab 4 open-ended lab for e-transfer also. Okay, so I already gave the video instruction and the explanation. So please make sure you go through. Don't do last minute. I'm giving you earlier so that you will have more time. So please do it well because it carries more marks. Okay, open-ended lab carries more marks because you're doing more work. So make sure you don't lose any mark. Okay, so that's what I want to say. Okay, so I think most of your friends already here. So we will start chapter 7, part 2 on the energy analysis on the closed system. Okay, so constant temperature, ideal gas. So previously we have seen constant pressure and constant volume. Okay, for closed system. Okay, so today we will see uh, in short, what is constant temperature about, especially for the ideal gas. Okay, if the temperature of an ideal gas system is L constant, okay, so if temperature is constant, we always call it as isothermal. Isothermal meaning constant temperature. Then we will use equation of state. So equation of state is PV equals to MRT. Okay, so this is equation of state. We always use to calculate ideal gas. Okay, so here M is constant, so mass is always constant in a closed system. Then R is constant, T also constant. So then the whole thing, so PV will become constant. So all of these are constant. So we call it as C. Okay, so this is the curve. So for your PV graph, you only have one line because different lines will indicate different temperature. Okay, so since this is isothermal, you only have one line. Okay, so the boundary work done. Okay, there are two ways of you to calculate the boundary work done for isothermal case. Okay, so the left hand side and also the right hand side. So all indicating the same thing. Okay, so it's based on the PV equals to MRT. So MRT equals to PV. So both are the same. But it depends. Okay, so depends on what information is given in the question. So you can choose which way you want to calculate the boundary work done. Okay, so you have this is the first formula. So WB equals to MRT ln V2 over V1. So this is the first formula. Then you have this formula. So V2 over V1 equals to P1 over P2. So it's coming from this formula. So you rearrange, you can get this. So if the information of pressure is given, then you can use this formula. Then you also have from this derivation on the right hand side. So you can have this formula if C is given, or you can use this, or okay, these are the same. Okay, sorry, P1 V1. If the information of P1 V1 is given, then you can use this. If the information of P2 V2 is given, then you can use this, because P1 V1 equals to P2 V2. So there are around 4 to 5 variations of formulas that given. So we normally use we choose based on the information given in the question. Okay, the above equation are the result of applying the ideal gas assumption for the equation of state. So we are considering it ideal gas. So ideal gas normally like oxygen, the normal air, then nitrogen or hydrogen. So we refer to the thermodynamic table I showed last time. Okay, so you can refer to the ideal gas table, and you can get all the parameters from the table. So for real gas undergoing the isothermal constant process, the integral the boundary work equation will be done numerically. So you will do the calculation. Okay, so heat transfer. So energy balance to this case. Okay, so U1, so internal energy 1 plus, because you take from this system, so right hand side, you are taking whichever is going inside, and U2 is going outside. Okay, so you know the boundary work done is the area under the curve. Okay, luas di bawah curve. Okay, so for ideal gas, so this is the equation that we have studied in chapter part 1. Okay, so U1 equals to MCV T1, and U2 equals to MCV T2. So this is the formula we got from the previous slide, previous part. Okay, so temperature is constant. So the temperature is constant, U1 equals to U2. Okay, so if you replace U1 equals to U2, so U1, U2, so you can cancel it. U1 and U2 is the same, so you can cancel. Then left Q equals to W. Q equals to W. So we know that for isothermal case, okay, in a case where the temperature is constant, the heat enters the system equals to work done by the system. Okay, Q equals to W. Okay, so Q equals to W. So kalau dalam soalan dia bagi tahu is isothermal, you can use this formula straight. Q equals to W. Tak perlu derive. Okay, but this is only for the ideal gas condition. So kalau dalam soalan iaitu berkaitan dengan ideal gas, and soalan bagi tahu is a constant temperature, then you can straight away use this. Okay, so it's only for the ideal gas and also isothermal case. Okay, so the heat added during the constant temperature process is converted into work, and the internal energy of the system remains constant. Okay, internal energies remain constant. U1 equals to U2. So the heat is transferred straight to the work. Okay, the systematic thermodynamic solution procedure. Okay, so this is one of the important part for the energy analysis because you need to do step by step. Kamu kena buat step by step so that you won't miss out anything. Okay, so sebab itu saya tulis dekat sini systematic. So systematic means step 1, step 2, step 3, step 4 so that you know what to do next. So we call it as a systematic thermodynamic solution procedure. Okay. So how you can do energy analysis practically. So methodical solution procedure, the thermodynamic problems are relatively easy to solve. Because normally we know the question will be given, then you need to calculate something. So if we follow this step by step, that is easier to solve. So each thermodynamic problem is approached the same way as shown in the following, which is the modification of the procedure given in the text. So these are the 6 steps. Okay, step 1. First, once you get sketch the system. Okay, lukis sketch. So lukis system. Jangan lukis 3D. 2D enough, but you need to get all the information from the question. Then you sketch the system, whether it's a piston or whatever system. Then show the energy interaction, whether it is entering the system, so Q in ataupun work in ataupun work out. So all you need to write in the uh, sketch. So that's the first step. The second step to determine the property relation. Property relation meaning, so what is the fluid used in the system? Whether it's a nitrogen or what. So if nitrogen, so you know that you need to use the ideal gas equation. Okay, so it's practically like that. So is the working substance is an ideal gas or real substance? So begin to fill up and fill in the property table. Okay, so this is something that you need to do. Second step. Then third step, determine the process. Process meaning whether it's a isothermal or constant pressure, constant volume. So these are some keywords that you need to extract from the question. I sketch the process diagram to continue to fill the property table. So number 4, apply the conservation of mass and conservation of energy principle. Okay, so you need to make an assumption. So using the conservation of mass and continuity equation. Okay, that's number 4. So bring in the other information. So the information whether like volume doubles, because we will check between initial state and also final state. So you check whether the question is saying the volume double or increase. So this kind of keywords, okay, from the question. Then number 6, so develop the enough equation, because you already know from step number 2. So what type of substance that you are dealing with. Then you choose the right equation to solve the unknowns. So whatever things that you don't know or the question is asking you to find, so you find in the step 6. Okay, so we will see few example of how we can use this. Okay, so satu contoh, one example. Okay, so here the question is saying 3 kilograms. Okay, 3 kilograms. So you know M equals to 3. So 3 kilogram of nitrogen gas. So so I encourage for you to take highlighter. Yeah, okay, so highlighter for your exam. So I like siap siap. Okay, so nitrogen. So nitrogen is an example of ideal gas. So you know that the system is dealing with ideal gas. So okay, 27 degrees Celsius and 0.15 million Pascal. Okay, so pressure is given, temperature is given, uh, compress meaning work is done on the system. So compress, macam ni. Okay, so isothermally, so meaning the temperature is constant. Okay, so if 27 degrees Celsius as initial state, so final state pun 27 degrees. So that is what we mean by isothermal. Then you see from 0.15 million Pascal increase to 0.3 million Pascal. Because you know, so kalau you compress, luas dalam ni keluasan, volume inside. Okay, isi padu dia berkurangan, so the pressure will increase. So you know it's a compression. It's a piston cylinder device. So yang ni untuk you sketch. So you know what to sketch. So it's a piston cylinder device. Macam ni lah piston. So determine the minimum work of compression in kilojoule. Okay, so you do the step like initial. Okay, so tulis system. System is a nitrogen contained in a piston cylinder device. So nitrogen is ideal gas. So tulis yang ni dulu. So based on the information you get from the question. Then the process is isothermal. Okay, or constant temperature. Okay, then locate the piston. So you're putting the force. So the work is compressing. So dari luar ke dalam. So you have a system here, so a system boundary, and inside here you have a nitrogen gas. Okay, so you dah lukis ni, lukis PV diagram. Okay, kita selalunya kita panggil as PV diagram, walaupun yang ini adalah curve. So it's a graph. But we will call it as a PV diagram. Okay, so we know that. So all the information from the question you can take here. So you can see it's a constant temperature. So meaning only one curve, so one graph. Then you know that. So you don't know the direction. So kalau you tak tahu direction, so you see the pressure or the volume. Okay, here no volume information given. So cuma ada pressure. So initial state. So P1 adalah 0.15 million Pascal. So P2 adalah 0.3. So meaning dari 0.15 increase ke 0.3. So meaning the pressure start dari kosong sampai tinggi. So meaning the curve is going up. So ini adalah state 1, ini adalah state 2. So it's going up because the pressure is increasing. Okay, so you already know this. Okay, since under the given condition nitrogen is ideal gas, so we use the ideal gas equation. So ideal gas equation, we know that PV equals to MRT. Okay, PV equals to MRT. Okay, then we go to, because the question is asking us to calculate the minimum work of compression. Okay, so the work, the equation for the work net work done is so net work done between state 1 to state 2, bukan 12 ya. So not 12. So 1 to 2. 1 to 2. So that's the indication. So you need to add other work involved plus boundary work done. So this is the equation. Okay, so we know that the other work is not present. So you only have a boundary work done. Okay, so this is from the previous derivation. Okay, so previous derivation. So we know, I think, okay, so you can take one of the formula here. Okay, so in this question, they choose this. So boundary work done between 1 to 2 equals to MRT ln V2 over V1. Okay, so for ideal gas in a closed system, so closed system meaning mass is constant. So M buang. So M1 equals to M2. M1 equals to M2. Then this is derived from the ideal gas equation. So you bawa M ke one side, so you can get this equation. So P1 V1 equals to RT1 equals to P2 V2 over RT2. So ini adalah the balance equation. So M1 equals to M2, so you cancel out. Okay. So we know that R is the constant, so you cancel out. So in isothermal case, temperature pun constant. So T1 pun sama dengan T2, so you cancel. So at the end, you ada P1 V1 equals to P2 V2. And then you rearrange, you dapat macam ni. So V2 over V1, so dekat equation ni, so you have V2 over V1. So you replace it with P1 over P2 because in the question, P1 over P2 is given. P1 and P2 is given. So you can better use this. Okay, so in your exam, so saya akan bagi all this equation. Okay. Macam tadi dia gunakan equation ni. Kemudian dia buat the ideal gas equation, then convert to this. So in the exam, I already give all this 4 to 5 formulas. So straight away you take this. So no need to do all these things. So straight away you take this. So straight away you can calculate. So boundary work done M equals to MRT ln P1 over P2. Kemudian ganti all the information. So M is 3 kg. So R is 0.2968. Okay, so R is you get it from the table. Okay, thermodynamic table. Okay, so pergi ke table 2. Table 2 I think for ideal gas. So straight away you find for tadi nitrogen. So for nitrogen gas, what is the value of R? So terus ambil. So you will get 0.2968. Okay, then T is tadi berapa? So 27 degrees Celsius. So in this formula is in Kelvin. So Celsius tambah dengan 273, 273. So 27 plus 273 equals to 300 K. So 300 Kelvin. Okay, ln. Okay, P1 over P2. So P1 0.15 million Pascal. So over P2 is 0.3 million Pascal. Okay, so you solve all this, you will get so negative 184.5 kilopascal. So the net work is ini adalah total work. So net work equals to 0. So other work is 0 plus boundary work done is negative 184.5 kilopascal. Okay, so if the question asks to find in per unit mass, so tadi M adalah 3. So 3 kg, so you just bagi dengan M. So negative 184.5 kilojoule divided by 3, so you will get so negative 61.5 kilojoule per kg. Okay, so the net work done is negative because the work is done on the system. Okay, so previously we have seen that work done generally if the system absorb any work, the energy increase. Tapi untuk boundary work done for isothermal case, so the W, so we saw the equation earlier. So Q equals to W. So whatever enters goes out. So it enter the system equals to work done by the system. Sebab itu kat sini the net work is negative because the work done on the system. So it's opposing whatever going up. So yang ni dia sebab equation dia is Q equals to W. Okay, so whatever masuk dia akan keluar. Okay, so during the compression process, so this is work done on the system. Yang ni dia negatif sebab dari luar dia masuk because you are compressing. So compressing. So the work done on the system is 184.5 kilojoule, or 184.5 kilojoule of work energy is required to compress the nitrogen. So kalau done by the system, dia akan jadi positif untuk isothermal case. Okay, so that's on this. Okay, so we see another example. Okay, so you try to relate with whatever we learned earlier. Okay, for this example, air is expanded isothermally. So yang ni kita berkaitan dengan air. So air also is under the ideal gas condition. Okay, so it's expanded. Expanded maksudnya from inside going out. So this is a correct one lah. So this is supposed to be a positive. Okay, so isothermal. So another term is isothermal. So it's a constant pressure, temperature. So temperature is 100 degrees Celsius. So P1 is 0.4. So P2 is 0.1. So we know that when the system expand, the pressure will decrease. So yang ni kita kena tahu. So kalau sistem dia besar, the molecule dalam sistem tu akan ada more space. So it won't be too pressurized. So kalau dia compress, so the pressure will increase. So P1 equals to 0.4 million Pascal. So P2 equals to 0.1 million Pascal. Okay, so in a piston cylinder. So it's a piston cylinder. So find the ratio of final to initial volume. So dari soalan ni ratio maksudnya the final to initial volume. So V2 over V1. So that is a ratio. Okay, so they ask to find the V2 V1, then they ask to find Q and also work W. Okay, so this is the question. So first you do, what is the system? System is a air contained in a piston cylinder device. So it's a closed system because no mass is entering. Okay, the process is a constant temperature process. Okay, so lukis yang ni, so a piston, then you have a system with a boundary air. So boundary work done, the only work done is the boundary work done. So T is constant, temperature is constant. So lukis graph, so PV diagram. So PV diagram, so you lukis only, since it's a constant temperature, only one curve. Okay, so now determine the arrow. You see the information in the question. So dari pressure tinggi, so P is higher here to P lower. Okay, dari kosong sampai atas. So we can see that the pressure is dropping. So the curve arrow ke bawah. So dari tinggi ke rendah. So pressure is from 0.4 dropping to 0.1. Okay, so dah lukis yang ni. Then you go to the property relation. Property relation, assume air is an ideal gas and use the ideal gas property relation with constant specific heat. So PV equals to MRT. So this is one of the formula that you can use using a specific heat. So sebab dalam ni dia ada temperature formula. So you can use this. So conservation of energy. So we know E in minus E out equals to the changes of the internal energy. So Q net minus W net equals to changes in internal energy. The system mass is constant, but it's not given. So system mass. So kalau nak gunakan formula ni, if you want to use this formula, so M is not given in the question. So automatically, so you take So you disregard. So you take per unit mass. So kalau you bagi sebelah kanan dengan sebelah kiri dengan M, so at the end you will get PV over M equals to RT. So M cancel. So you can straight away find work and heat transfer per unit mass. Okay, so if we calculate first, okay, this is from the derivation earlier. So we know that boundary work done equals to MRT ln V2 over V1. Okay, so it's a conservation of mass principle. So for an ideal gas in a closed system, so closed system mass is constant. So M1 equals to M2. So M1 equals to M2. So we know that. So this is the remaining formula from PV equals to MRT. So P1 V1 over RT1 equals to P2 V2 over RT2. Okay, so we know R is a constant, so cancel. So temperature pun constant, so cancel. So last ada P1 V1 equals to P2 V2. So you rearrange dapat macam ni. So V1 go here, so P1, P2 goes here. So dapat macam ni. So the question is asking us to find the ratio of final to initial volume. Ratio of final, so final volume adalah V2 over V1. So equals to P1 over P2. So replace the information 0.4 bagi dengan 0.1. So the ratio is 4. Okay, so we already answered the first part. Ratio of the final to initial volume equals to 4. Okay, then we go to the second part. So the work expression per unit mass. Sebab value mass tak diberi, so mass is not given. So you find per unit mass. Okay, so small w, because per unit mass equals to bigger w over m. Okay, so this is from the previous equation derivation. So RT ln V2 over V1. Okay, so you replace all the information. Okay, for normal air, R is 0.287. So you get this from your table, thermodynamic table. Okay, T is 100. So 100 plus, so T, so not in Celsius, so it must be in Kelvin. So 100 plus 273. Okay, so okay, this is K. So ln, so V2 over V1, we know, we calculate earlier 4. Okay, solve this, dapat 148.4. So 148.4 kilojoule per kg. So make sure the unit is per unit mass. Okay, so you already got this. Then the net work per unit mass. So W net equals to, so other work is 0 and the boundary work is 148.4. Okay, so you finally will get the net work done is 148.4 kilojoule per kg. Now continue the conservation of energy to find the heat transfer. Because the question asks you to find. Okay, so yang ni dah cari. So heat transfer, work already fine. So heat transfer now. Okay, so for heat transfer, you use this formula. Okay, so this is from the previous chapters. Okay, so internal energy between 1 to 2 is mCV T2 over T2 minus T1. Okay, so equals to 0. So internal energy is 0 because T2 minus T1. So isothermal. Okay, so isothermal. So yang ni akan jadi kosong. Kosong. So the whole equation becomes 0. Okay, so the heat transfer per unit mass equals to Q net equals to Q net per M. Okay, this is to find the per unit mass. Okay, so this is from the previous equation. Q net minus W net equals to changes in internal energy, which is equals to 0. Okay, so yang ni bawa ke sini, so net equals to W net, so which is 148.4 kilojoule per kg. So the heat transfer to the air during the isothermal expansion process is equals to so yang ni the air meaning is entering the system. So because dalam system tu ada air kan, udara. So the heat transfer to, so Q in equals to W out, W out. Okay, so you already find all the information. So all these solution are following these steps. So all these steps. So what step by step? So when you do step by step, you won't miss out important points. Okay, so that's on the two examples. Okay, so we have seen the two example. So now we enter to another subtopic. We call it as a polytropic process. Okay, so in an energy analysis, so there's a term called polytropic process. Okay, so for polytropic process is one in which the pressure volume relation is given as so you always use this. So if the question is saying it's a polytropic process, ataupun you have this PV to power of n. So if you see this, the relation in the question, information in the question is related to power of n, then you know it's a polytropic process. So kadang-kadang dalam soalan dibagi tahu polytropic process, or they only put PV to power of n. Kalau nampak n, automatically you know it's a polytropic process. Okay, so the equation is PV to power of n equals to constant. Okay, so equals to constant. So in this case, so the heat energy is lost and work is done by the system. Okay, so this is the relation. Okay, so you know the boundary work done is the area under the curve. So the curve is PV to power of n equals to constant. Okay, and the value of n. Okay, the exponent n. Okay, so we have a few indication. So we have a value from minus infinity to plus infinity. So depending on the process. So you need to get the keyword from the question. So you find the keyword whether if the question is saying the pressure is constant ataupun isobaric. So if the term like isobaric, so the value of n equals to 0. So maksudnya, so PV to power of 0. So if the question says it's a constant pressure. So if the question says it's a constant volume, so the value of n equals to infinity. Okay, constant volume. So if the question say isothermal or ideal gas, so you take the value of 1. If adiabatic, meaning no heat transfer, Q equals to 0. Alright, and it's an ideal gas, so you take the value of K equals to Cp over Cv. So value of Cp and Cv you can get from your thermodynamic table. Okay, so you can get this. So here K is the ratio of the specific heat as constant pressures. So Cp is constant pressure to specific heat at constant volume. Okay, V here is constant volume. The specific heat will be discussed later. Okay, so here, so if it's a polytropic process, so you need to use this formula. So this is the derivation. So you replace it. So P this boundary work done is calculated based on this equation earlier. P V to power of n equals to constant. So P equals to V to power of n pergi ke bawah. So go down. So constant over V to power of n. Sebab itu you dapat macam ni. So then this is the integration. So if you integrate this, so constant you bawa keluar. Okay, so 1 over v to power of n. So you integrate, you will get the equation like this. Yeah, and this equation is also related to this. So related to this, so if n cannot be uh, yeah, 1. So kalau dia 1 minus 1, it becomes 0, then the equation become error. Okay, so it's error. So if the case is not 1, if the case is 1, then you take this. Okay, so you refer to page 3 earlier. Okay, so this from the derivation, PV equals to PV times with ln V2 over V1. Okay, for an ideal gas undergoing polytropic process, the boundary work is, okay, so you have a few equation that you can use. Okay, this from page number 3. So refer to page number 3 earlier. Okay, from here, so we know that you can use this formulas to convert between parameters. So if the question give P1 over P2, so you can take this. If T2 over T1 over T2, so you can take this. So you can see the power is changing. So n, so here n minus 1. So T1 over T2 equals to P1 over P2. So you can choose either one. Okay, we will see in the example after this. So how you can choose this. Okay, so we'll see the example. So air is a closed system. Okay, so you know it's a air. So it's a closed system. So meaning the mass is constant. So undergoes a process from initial state. So P, so 3 bars. So 3 bars, volume 0.1 meter cube to the initial final state. So final state V 0.2 meter cube according to the relation. So you see, the question didn't mention it's a polytropic process. Tapi dia bagi tahu macam ni. So PV to power of 1.2 equals to constant. So here n. So V to power of n. So sama dengan V to power of 1.2. So n is 1.2. Okay, so they asked to plot the PV diagram. So determine the final pressure. So P2, okay, the work done during the process in kilojoule. Okay, so draw. So you draw the PV diagram because they asked to draw the PV diagram. Okay, so it's isothermal. So it's only one graph. So pressure is 3 bar. Okay. Okay, so since you don't know the final pressure is increasing or decreasing, so you just put from 1 to 2. So just moving downward. Later we will see whether it's minus or positive. Okay, so that's a PV diagram. So we try to find the pressure, final pressure P2. So the process is known as a polytropic process with n equals to 1.2. So V to power of n. So n is 1.2, and the pressure at the final state can be obtained as the follows. Okay, so P1 V12, because the formula is PV equals to constant. PV to power of n equals to constant. So P1 V1 to power of 1.2 equals to P2 V2 to power of 1.2 equals to constant. So you can use this formula. Okay, then we can get this. So P2 equals to P1 V1 over V2 to power of 1.2. So replace all the information. Okay, so P1 equals to 3 bar. So V1 equals to 0.1. So V2 equals to 0.2 to power of 1.2. So finally you get 1.31 bar. Okay, so this is in the pressure because for this pressure, they only ask to determine. So you can just leave it as a bar. So or if you want to convert it to Pascal, times with 10 to power of 5. So any convert to Pascal. So 10 to power of 5. Okay, so that's the first part. Then part 2. So the work during the polytropic process is given by, so W equals to P2 V2 minus V1. So this is from page number 16. So refer back. Sorry, not page number. I think page number 15. There. Okay, sorry, page number 16. Okay, page number 16. So you can get the formulas from here. Betul lah, on page number 16. Okay, page number 16. So you just replace all the values. Okay, so you will get the work done is 19 kilojoule. Okay, the work done is a positive work done, so 90 kilojoule for expansion. Okay, because system is doing. When system is doing, so your boundary work, it will be expanding, so it's a positive. Okay, only for this isothermal case. Okay, therefore the work is done by the system. So work is going out from the system. Okay, so it's a positive. Okay, so that's one example. So we'll see another example. So the combustion gases in a petrol engine cylinder are at 30 bar. Okay, combustion gas. So and 800. So the P1 is 30 bar and T1 is 800 degrees Celsius before expansion. And keyword adalah before expansion. So meaning is the initial state. So the gases expand through a volume ratio V2 over V1. Yang ni dia bagi tahu volume ratio. So volume ratio is given. So V2 is 8.5, V1 is 1. Okay, so you can take a direct relation. And occupies 510 centimeter cube. So make sure when you use for calculation, you convert it to meter cube. Okay, after expansion. So volume, so V2 8.5 almost equals to 510 centimeter cube. Okay, when the engine is air cooled, the polytropic expansion index is N. So question can say polytropic. So N equals to 1.15. Okay, so what is the temperature and pressure of the gas after expansion? So after expansion means T2 and P2. And what is the work output? So work done. So considering air as a perfect gas, so you can use ideal gas equation. For the polytropic process, the property relation, so you can get this from this equation. So tadi kita tengok kan. So this page number 17. So you can use all this. Okay, so for this case, we use this, the second one. So T1 over T2 equals to V2 over V1 to power of N minus 1. So you take this. So you want to calculate T2. So you rearrange this. So you rearrange this, you akan dapat macam ni. So T2 equals to T1 V1 over V2 to power of N to power of N minus 1. Okay, so you replace all the information. Okay, T1, so make sure not using 800 in Celsius. You need to convert it to Kelvin. So 800 plus 273. So you dapat 1073 times with, so V2. So the equation is V2 over V1. So here V1 over V2. So you terbalikkan dia 1 over 8.5. So 1 over 8.5. So N is 1.15. So 1.15 minus 1. Okay, you solve this, you will get the value in Kelvin. So 778.4 K. So but they didn't say, you can leave it in Kelvin if you want. So if you want to convert it into Celsius, because here is Celsius, so you just need to minus 273. So you will get 505.4 degrees Celsius. Okay, so that's the first part. We already find T2. So now we're going to find P2. So P2, you use this equation. Okay, from P17 also, use this equation. Okay, I think this is the latest lecture note. Okay, I already updated in Google Classroom. So make sure you download the correct one. So because I saw this page number in the previous slide I gave, it put page 16. Then you will confuse. Kenapa page 16 tak ada? Because I think page 16 we are talking about this. So it's not about this. Okay, so please update. Okay, or take the latest lecture note from the Google Classroom. Okay, so you take this from this equation, P1 over P2 equals to V2 over V1 to power of n. Okay, so you replace all this. So P1 is 30 bar. So V1 over V2 is 1 over 8.5. N is 1.15. So you solve this, you will get the value in bar. Then if you want to convert to Pascal, you just times with 10 to power of 5. Okay, so you'll get the value of P2 equals to 2.56 times 10 to power of 5 Pascal. Okay, now the question asks to find the work output. Okay, the work output. Okay, so V2 is given 510 centimeter cube. Okay, so you convert it. So 510 times with 10 to power of -6. So this is a conversion, direct conversion. So to convert centimeter cube to meter cube, so you just need to times with 10 to power of -6. Okay, so V2 over V1 we know 8.5. So getting from here, so 8.5 over 1, so it's 8.5. Okay, so you dapat yang ni. So V1 is, okay, you just need to replace all this information here. Okay, so V1 go here. So this 510 times 10 to power of -6 divide by 8.5. Sebab itu you dapat macam ni. Okay, so you get so V1 equals to 60 times 10 to power of -6 meter cube. So V1 you already find. Okay, so you already find V1. Then you replace it with the polytropic expansion. I think so one of this formula you can take. Yes, I think in the question they took this formula. So P2 over this formula. So here we take a larger PV minus smaller PV because we want to know the amount, so not the direction. Okay, so larger PV minus smaller PV. So P1 V1 minus P2 V2 over n minus 1. So you replace all the information. So you'll get 330 joule. So which is 0.33 kilojoule. Because the question asks, okay, the question didn't ask. I think the previous question they asked the work done in kilojoule. So here it's not asked. So you can just leave it in joule. Or if you want to convert to kilojoule, you just divide by 1000. So you will get 0.33 kilojoule. Okay, so end of chapter 7 part 2. Okay, any question? Okay, I think that's all. It's in less than 1 hour. Okay, so any questions on chapter 7 part 2? I supposed to give this as a ad puzzle video, but I just want to discuss in class. So also you see the chapter is quite short, but it's okay. So I think we already managed to cover within 1 hour. So you have any question? Ada soalan? Okay, so if no question, announcement again. So next week we will have physical lab, okay, in thermodynamic lab. So for lab number 3, so I already uploaded all the lab module. Okay, I also uploaded the assessment forms. Okay, please fill in assessment form. Total 4 assessment form contribute to 5 marks of your lab. Okay, so please fill in all the assessment form given in the Google Classroom. Then I also given you lab 2 last time. I think before your midterm break. Okay, I already given you lab 2. Okay, it's an open-ended lab, so I am mark. So you need to develop the whole lab module. Okay, listen to the instruction video given and do the lab module as well as the lab report, and you need to submit. Okay, I am marks. I think 5 marks alone for lab 2, and lab 4 also the same open-ended lab. So e-transfer. Okay, so lab 2 is Bernoulli's equation. So try to do the lab from now. So don't do last minute. So that's why I give you earlier so that you'll have more time. So the submission date for the open-ended lab is the final week. This final week, week number 14. So now is week number 11. So at 11, 12, 13, 14. So you have 4 more weeks, almost like 1 month to complete the open-ended lab on Bernoulli's equation and also e-transfer. So start to do now. Okay, don't skip. Okay, so that's one thing. Then I already finished mark your test 1. How to say? Some you scored well, some didn't do well. Okay, so I supposed to return back your answer sheet today, but since we didn't do physical class, so maybe next week I will pass back to you so that you can see your performance. Okay, and midterm exam is 15 marks. Okay, so I saw some didn't attend, so I'm not going to do a retest. Okay, so you consider like lose the marks 0. Okay, for midterm exam. Okay, all my assessment I won't do. I won't give back. Okay, uh, I think at quiz 1 I still owe you. So I think whoever want to do quiz 1, so that one I will do because it's just like a game format, just to enhance your understanding. So apart from that, all the other assessment is following the due date. Okay, so if you didn't submit, so I'm not going to bother as well because you don't bother about submitting. So I also not really bother about to ask you back. So saya takkan kejar you. Oh, please submit, please submit. So if you lose mark, you lose mark. So if not enough mark, you just will repeat the subject. You will see me back in the coming year. Okay, so that's it. Okay, so that's some announcement. So I think apart from that, so nothing for this week. Okay, no at puzzle. So no Friday class also. So you just can relax. Okay, so I will upload this video in YouTube. Please listen back if you don't understand. And I think that's it. So we will see next week. Okay, so thank you so much. Okay, so stop the recording.